off a little. I'm sure
Okay,
that's it.
good. Okay, page 43, chapter 3. So, today we're going to define a function that I'm going to waste a certain amount of time not using what we would expect our notation to be. I'm going to define a function called exp of z. It's going to be equal to e to the x cosine y plus I sine y. Now, this is e to the x times e to the iy, which really means that looks like we're doing e to the z. But I want to hesitate on this for the time being and just keep this notation for cos. So first off, this exponential function seems a bit odd. It has this cosine and sine in it and doesn't seem like a natural definition, but when you see it over here in this notation, it seems quite natural. Now, theorem or proposition 316 says that a couple very things happens. For all z1 and z2 in the complex numbers, everything about the exponential function is going to work as if it was written that way. And so exponential of z1 times the exponential of z2 is the exponential of z1 plus z2. Next, 1 over the exponential of z1 is equal to the exponential of minus z1. Next, the size of this function, the exponential of z1, well, that's just the unit circle. It's pretty clear that it's going to be equal to the size of that e to the x, which is the exponential times the real of z. Now, some that are a little harder to prove, for example, the exponential of z1 is never 0. A little bit harder, the derivative with respect to z of the exponential of z is going to be the exponential of z. Now, again, I want to stress that we're not going to think of it this way. We've defined our function this way, and if we check these properties, almost all of these are pretty much immediate. So let's do one or two of them. So, for example, let's define f of z is the exponential of z, and let's determine the partial of f with respect to x. Well, the exponential of z is e to the x times the cosine of y plus I sine of y. And when we do the partial with respect to x, why, we're just going to get the exponential back, and that's a constant. So if the Cauchy-Riemann equations are satisfied, this is going to actually show that the function is its own derivative. Oops, which is kind of nice. But does it satisfy the Cauchy-Riemann equation? So the partial of f with respect to y is going to be the partial with respect to y of e to the x cosine y plus I sine y. Now we ignore the e to the x, take this derivative, we get e to the x. Derivative of cosine is minus sine. Derivative of sine is cosine. And then now I times the partial of f with respect to y with a minus will be e to the x, and the minus minus I will be I sine y, and the minus I cosine will be cosine of y. And lo and behold, Cauchy-Riemann equations are satisfied. And these are continuous functions, hence this exponential function has the property that its derivative is itself. Well, if we have this thing called the exponential function of z. One would kind of like to know, does it behave exactly like the real function? Well, the answer is not quite. If we restrict z to just be a real number, well then clearly f of a real number is going to be e to, well, the real number will be the r and the cosine of 0 plus I sine of 0, and lo and behold, we'll get e to the r, which is exactly how we want it to behave. That when you plug in an x, you get out e to the x. So it's an extension of the real function. Well, as soon as we have a function, we kind of like to see how it behaves. And we like to draw pictures. So what we just discovered, if this is our function, e to the z, the exponential of z, and here's the complex plane. Well, what's the image of this line? That's the real line. Well, it gets mapped to the complex numbers that are e to the r, which are all positive numbers. So where do all the positive numbers get mapped to from here to here? Well, they're along here. All right, so let's take another spot here. Let's try a vertical line. Where does this get mapped to? So that's where the x equals 0, and so, well, e to the 0 cosine of y plus I sine of y, that'll be gone. And so cosine of y plus I sine of y, and y is going to vary. So it seems that we're going to get some funny values here. So what are these funny values? Well, y varies from minus infinity to infinity. This is a unit circle. So we go around this unit circle several times. Now, let's take another vertical line. They're most interesting. Take a vertical line here at some distance x away from the origin, and then let y vary. Well, then the image of the exponential will be a fixed value of e to the x, cosine of y plus I sine of y. And so if you keep this fixed here, this will then circle around again. And so again, we're going to get a circle, but this guy's radius is the e to the x value. So we're going to get circles for every vertical line. And for this one, we got that horizontal. Let's see what another one looks like. Let's take this line. Let's say the line at x plus pi halves I. What happens in its mapping? Well, x plus pi halves y, when stuck in, we'll get e to the x, and then we'll get cosine of pi halves plus I sine of pi halves. This will be a 1, this will be a 0, and so we're going to get e to the x times I. And this goes from, 0 to infinity, so we're going to get this line. So it seems that first we got this line from 0 out to infinity. We got this line. It seems that we're getting lines originating in the origin going out, and we're getting circles around it, that this is the image of this hex, of this hatch. All right, so we have kind of some pictures of what the image looks like. Let's now take a look at what we can do with this exponential function. Well, before we do much more with the exponential function, we're going to use the exponential function to define two more functions, the sine of z and the cosine of z. So let's take the sine of z and define it to be equal to, and we're going to take it as 1 over 2i times the exponential of iz minus the exponential of minus iz. Seems like a very strange definition, and we're going to do cosine of z, and we're going to define it to be 1/2, not 1 over 2i, and we're going to do the exponential of iz plus the exponential of minus iz. Now, those of you that have seen hyperbolic sine and hyperbolic cosine, you'll recognize that this looks very similar to them. Now, why am I going to define these two functions in this way? Well, first off, we noticed that when we did e to the z and we restricted to the real line, we got e to the x. In other words, the e to the z was an extension of the function e to the x. Is it possible that if I put real numbers into these expressions, that the sign of a real number using the complex formula and the complex exponential will match the sign of its real value? So let's give it a shot. Let's put in the sign of an x plus 0i. Complex. Well, by definition, it's 1 over 2i times the exponential of I, x, where x is the only real part, minus the exponential of minus I, x. And now we're going to use our definition of the exponential here. Our exponential function was the e to the real part of the complex number times the cosine of the imaginary part plus I sine of the imaginary part. Now, x was the real part of the original input variable, but now ix is the real part of the input to the exponential. So the exponential of this solely complex number here is cosine of x plus I sine of x. Now, over here, it's going to be the same thing with minus signs in, so cosine of minus x plus I sine of minus x. And we're going to get 1 over 2i. And cosine of, by the way, cosine of minus x is the same as cosine of x, so these cancel. And sine of minus x is minus sine of x, so that pops out here, and we get 2i sine of x. Lo and behold, we get the sine of x as a real number. So this formula extends the sine function into the complex plane when you put in this formula for the sine of a number, where the number is a complex number, but if you restrict it to a real number, it matches the sine of the real number, because we use sine and cosine of the real functions to define the exponential. Well, now this behooves us, fancy word, to look at properties. And what's amazing about this, Proposition 317, says that everything that we know about sine and cosine that we've just defined via the exponential function now hold true. In other words, if you negate a complex number with the sign, you get the minus of the sign without it. Same thing with the cosine. The cosine of a minus z will be the cosine of z. In other words, the properties of sine and cosine appear to be staying the same. Now, there's not really a good way to interpret periodicity in the complex plane, but if there is a number that you add to a function and it is repetitive, then we can call that the period. Number might be real, number might be complex, who knows? Well, turns out the sine of z plus 2 pi is the sine of z, and the cosine of z plus 2 pi is the cosine of z. So sine and cosine as complex numbers are periodic from any complex number, 2 pi to the right, 2 pi to the right, etc., any multiple of 2 pi. Now, if we extend our definitions now to, say, the tangent of z, p defined as the sine of z divided by cosine of z, and all of the other trig functions, then it would be nice to know, are they behaving nice? And the answer is absolutely. They're behaving just like they did before. In fact, let's just write down one of the facts about the sine from pre-calculus. The sine of the sum of two angles, well, in the complex, it's going to be the sine of the first, cosine of the second, plus the sine of the second, cosine of the first. In other words, oops, all of a sudden I started adding parentheses. In other words, it extends the law of the sines. In fact, it has extended all of the things that we've been seeing almost identically. Sine squared of z plus cosine squared of z equals 1. And again, that can be done from first principles. Here's the cool one. The derivative with respect to z of sine of z will be cosine of z, and the derivative with respect to z of cosine of z will be minus sine of z. Absolutely everything that we did with sine and cosine before are being repeated in the complex plane. This tells us that we did something very nice with this very strange definition long ago, that if this is called the exponential function and this is called the sine and cosine, then everything that we knew about the sine and cosine before still apply in the complex plane. The derivatives, the exponential, is the exponential. It looks like what has happened here is we have found a way to define exponential, sine and cosine in the complex plane, which are true extensions of the exponential function, the sine function, the cosine function that began in the reals. So maybe the correct way to look at it is that the reals was just a restriction of the strange functions that we had before that we are now just actually learning about. We're almost to the point where we're explaining why we chose e to the exp for exponential, and why I didn't want to write down e to the z right off the bat. And there's going to be a couple reasons for this, as we're going to see in a moment. However, the next thing I'm going to do is I'm going to talk about the inverse of this function. But it's not right to talk about an inverse of a function without knowing if it's one-to-one. But something strange has happened with the exponential function. It turns out the complex exponential function isn't one-to-one, even though the real exponential function is one-to-one. So, let's take a look at this. The exponential of z plus 2 pi. In other words, take a z value and then look at its exponential value and then look at it, not up by 2 pi, right by 2 pi, and see what value it is. So, by definition, exponential of z is going to be the e to the real part of the z plus 2 pi times the cosine of the imaginary part of z plus 2 pi plus I times the sine of the imaginary part of z plus 2 pi. Now that's the definition, e to the x cosine y plus I sine y, where this is the one that's going in. Well, e to the real part of x plus 2 pi plus yi is just this portion, e to the x plus 2 pi. So continuing here, we were looking at f of z equals the exponential of z, which I really would like to soon be just thinking straight up as e to the z. This real number e raised to a z power. But the fact of the matter is we don't have a complex number raised to a complex number definition, nor do we actually have a real number raised to a complex definition. We've been using e to the x as real, cosine of y as real, and we've been defining complex functions in that very specific way, but we've not defined a real to a complex power, nor have we defined a complex to a complex power. We have possibly defined a complex to a real one. We should take a look to see if we know how to do that. So, let's see what properties this has that might be odd. And there's one property that is quite odd. And that is, if here's a value z, we know this exponential function maps it someplace. So here's that function f of z. And it turns out that if I go up to z plus 2 pi I, guess what? This is going to map to the same point. We are not going to have a one-to-one function. So to see this, we're going to calculate the exponential of x plus yi plus 2 pi I. That's the x plus yi, that's the z. Well, this will be the exponential of x plus, factor out the I, and it's y plus 2 pi. And now by definition, the exponential of a real plus a real plus an imaginary time, and yi is e to the x, and then it'll be cosine of y plus 2 pi plus I sine of y plus 2 pi. But lo and behold, this is the real function cosine y, this is the real function sine y, which is the exponential function of z. So this function is periodic, going up and down. It's exponential going right and left. It's very strange. It isn't quite what we necessarily would have expected it to be, seeing how it works so nice for this exponential function to define sines and cosines. Now, we're actually heading to defining a complex number to a complex number power. But before we get there, we do need the logarithm function. But we just saw that the exponential function isn't one-to-one. So if we find a domain that the exponential function is one-to-one, well, then we got the shot of finding a logarithm function as its inverse. So first off, let's find some domain inside of the complexes so that our f of z is 1, 1. Then let's search for, and I'm going to use a capital L, log of z, that has the following property, that when that function, capital L log of z, is put into the exponential, that we'll get the z back. And when we take that logarithm of the exponential with the z in, we'll get the z back. Now, how do you actually find such a function? I mean, it seems you've got to make something up out of the clear blue sky. But it actually isn't that hard to do. If you start with this expression right here, this equation, if that's what you want, why don't we put the definition for our exponential function in there, and we say we want a log of the exponential of z, which is e to the x cosine of y plus I sine of y. And we realize that this is nothing more than a real number times what we call e to the I theta, where y is theta. And I just want to identify it that way for a second. And what the answer that we want to get out of here is we want this to bring us back to where we started. And where did we start? We started at z